Hello students, today we are going to discuss a very important topic in tree data structure, that is AVL tree. Now in this lecture we will discuss what is AVL tree. We will discuss about the AVL rotations that is needed for balancing the binary search tree, or you can say AVL tree, and after that we will discuss how a value is inserted into an empty AVL tree. Now first of all, the question comes, why it is so called? It is named on the name of its inventor. The first author was Adelson Walensky, and from that name we have taken A and V, that is AV, and the second author was E. Landis, and from this name we have taken L. So that's the reason it is called AVL tree, and it is developed in 1962. AVL tree is a self-balancing binary search tree. That means it can balance itself, and it is a special kind of binary search tree, because in binary search tree there is no balancing factor, but here at each node balancing factor is also associated. It is also known as height balance binary search tree. Then what is the meaning of balancing factor? According to balancing factor, in an AVL tree, at each node, height of left subtree minus height of right subtree, that should be less than equal to 1. That means the difference between height of left subtree and height of right subtree, that can be 0, that can be 1, or that can be minus 1. If we are getting these values at each node, then we can say tree is balanced. If we are getting any other value except these three values, then we can say tree is imbalanced at that particular node. We can understood in a better way with the help of this example. This is for example, this is a binary search tree. What is the property of binary search tree? A tree is called a binary search tree if value at each node is greater than from its left side values and less than from the right side values. We can check here in this example. 100, that value at this node 100 is greater than from these side nodes and less than from right subtree right node. In the same way, if we are checking at this node, 50 is less than 25 and greater than from these side values. In the same way, if I am checking this property as 150, that is 150 is less than 125 and greater than 175. Now the question comes, how balancing factor is calculated? Now, as we know, balancing factor means height of left subtree minus height of right subtree. Then for leaf node, balancing factor will be always 0 because there is no left child and right child. This is also a leaf node, that is also 0. This is also 0. Now, for example, we are calculating balancing factor at 75. Then height of left subtree. This is the left subtree, that is height 1. And this is right subtree at node 75, that is 1 minus 1 equal to 0. This is also a leaf node, that means balancing factor is 0. If we are calculating balancing factor at node 50, then at node 50, this is the left subtree and this is the right subtree. It means from that node to the deepest leaf node. That is height is 1, this is height is 2, 1 minus 2 is minus 1. In the same way, if we are calculating at 150, the height from left subtree is 1, right subtree is 1, 1 minus 1 is 0. If we are calculating this balancing factor as node 100, Then from this node, this is the deepest leaf node, that can be 65, 85. The height is 3. And in this, height is 2. That is 3 minus 2 equal to 1. At each node, we are getting these 3 values. That means tree is balanced. If we are getting any other values except these 3 values, then we will say that tree is unbalanced at that particular node. Now to balance the tree, we apply the different kind of rotation as per the requirement. A tree will be unbalanced if we are inserting a new value or we are deleting some existing value. In that case, tree can be unbalanced. Now to balance that tree, we will apply different kind of rotation. Now in AVL tree, there can be 4 kind of rotation. The first category is single rotation. In this case, we are rotating a tree at a particular node only in a single side, or that can be double rotation. We are rotating the tree. We are rotating the particular node double time. That is double rotation. In single rotation, we will rotate only single time. That can be left rotation. That is called LL rotation. We will discuss all these with the help of example. That can be right rotation. That is called RR rotation. In double rotation, there are 2 categories. That can be LR rotation. That means first of all, we will rotate left side, then we will rotate right side. And another category is called right left rotation. That means first of all, we will rotate right side, then we will rotate left side. Now these 4 rotation can be understood in a better way with the help of examples. Now for example, we have to insert these 3 values. First of all, we have to insert 1, then we have to insert 2 and then 3. When we are inserting 1, then tree is balanced because its balancing factor is 0. Then after that, we have to insert 2. In that case, tree is also balanced because if we are calculating the balancing factor at this stage, this is 0, that is leaf node. Height of left subtree, that is 0. Height of right subtree, that is 1. 0 minus 1, that is minus 1. If we are getting value 0, minus 1, 1, that is tree is balanced. But if we are inserting 3, okay, according to binary search tree property, all the values in the right side should be greater than from the root node. So then definitely 3 will be this side. After inserting the value 3, tree will be unbalanced. Why we are calling so? We can check it. The balancing factor is 0, that is minus 1. Here, right side, tree height is 0. This side is 2. So 0 minus 2 is minus 2. That means tree is unbalanced at root number 1, node number 1. Now we have to balance this tree. Now we have to understand one thing. Tree is unbalanced when we inserted new node, that is 3. Then we will go from that node to that node. From that means it is unbalanced 1, and we will go to that side due to which tree is unbalanced. So that is 2 is the right side of 1 and 3 is right side of 2. We are getting 2R. In that case, we will rotate tree into the left side as you saw on the diagram. If we rotate, then definitely we are rotating like this. Then in that case, 2 will become the root and 3 will come up like this, and 1 will come this side. Now we can check the balancing factor, this 0, 0, 1 minus 1, 0. That means tree is balanced. So this kind of rotation we are calling LL rotation. we should keep in mind one thing. If we are getting 2R, always we have to apply the left rotation. The next rotation is called RR rotation. For example, we are inserting these three values. First of all, we have inserted 3. After inserting 3 is balance because balancing factor is 0. And we have to insert 2. Then we will compare 2 with 3. That will come into the left side. That is 2. Still 3 is balanced. That is 0 or that is 1 minus 0, 1. But if we insert value 1, 3 will become unbalanced at node number 3. Why we are calling so? The height of left subtree is 2 and height of right subtree is 0. 2 minus 0, that is 2. This is 0, this is 1. That means tree is unbalanced at node number 3. Now tree is unbalanced when we inserted node 1. Then in that case, we will, where tree is unbalanced, we will go that node to that node due to which tree is unbalanced. That is left. 2 is the left of 3 and 1 is the left of 2. We are getting 2L. In that case, we will rotate tree in the right side. We will rotate, then it will be like this. That is, we are rotating in the right side. That is, 2 will become the root, 1 will become this side and 3 will become this side. Now tree is balanced. How we can see? We can check by calculating the balancing factor of each node. That is, balancing factor of this node is 0, 0 and height of left subtree is 1. Height of right subtree is 1. 1 minus 1, that is 0. That means tree is balanced. Third rotation is called, that come in the category of double rotation. We are rotating double time. First of all, we are rotating in the left side, then we are rotating in the right side. It can be understood with the help of this example. Suppose we have to insert these three values. First of all, we have to insert 3, then 1, then 2. Then in that case, first of all, when we insert 3, tree is balanced. Then we have to insert 1 because 1 is less than 3. This will come as a binary search tree property. It will come in the left side. If we are calculating the balancing factor, this is 0 and this is 1. 1 minus 0, that is 1. But if we insert 2, that means if we are inserting 2, that means we will compare 2 with 3. 2 is less than 3. Then we will compare 2 is 1. That means 2 will come at the right side of 1. When we insert value 2, tree will be unbalanced. Why we are calling so? Why we are saying so? We can calculate the balancing factor of node. That is, balancing factor of 2 is 0. Balancing factor of 1, that is 0 minus 1, that is minus 1. And the balancing factor of 3 is 2 minus 0, that is 2. That means my tree is unbalanced at node number 3. Tree is unbalanced when we inserted the value of, that is third node, value of 2. That means our tree is unbalanced at 3. Then we will go from that node to that node due to which tree is unbalanced. So that is the left. 1 is the left of 3 and 2 is the right of 1. Now in this case, if we are rotating tree like this, then it will become like this: 1, 3 and 2. In this case, tree will be balanced, but our BST property will be violated. What is BST property? At each node, its value should be greater than from left side child. That is, this side value should be less than from this value, and this value should be greater than from the root node. That is okay, but this condition is violating. That means here we have to apply double rotation. Now in this case, first of all, we will apply the left rotation, and left rotation will be applied where node is node is unbalanced, at that below node we will apply the rotation, that is left side. That means if we are applying rotation, first of all left rotation, then it will be like this: 3, 2 and 1. That means we are freezing this part and we are rotating like this. That will be 3, 2, 1. That is first rotation. Second rotation is right one, because tree is unbalanced at node 3. That will be, if we are rotating it at 3 as a right rotation, it will be 2, 3 and 1. Now tree is balanced. How we can say? The balancing factor of 1 is 0, balancing factor of 3 is 0, and balancing factor of 2 is also 0. That is height of left subtree and height of right subtree. The difference between these two is 0. 1 minus 1, that is 0. Now tree is balanced. The next rotation is RL rotation. That is, first of all, we will rotate the tree at a particular node in the right side. Then we will rotate the left side. Suppose we have to insert these 3 values. That is, first of all, we have to insert 1. After inserting 1, tree is balanced because balancing factor is 1. Then we have to insert 3. We will compare 3 from 1. Then it will come at the right side of 1, according to the binary necessity property. Then we have to check the balancing factor. Tree is still balanced because it is balancing factor, that is 0. That is 0 minus 1 minus 1. But if we insert 2, in that case 2 will be the left child of 3 according to binary necessity property. Now tree is imbalanced at node number 1. How we can see that? We can check the balancing factor. The balancing factor of 2 is 0. Balancing factor of 3 is 1. Balancing factor of 1 is minus 2. The height of left subtree, that is 0. Height of right subtree, that is 2. 0 minus 2, that is minus 2. That means tree is unbalanced at node number 1. Now, it is unbalanced when we insert node number 2. Now we will go from that node to that node, that is the right and that is left. Now first of all, we will rotate the tree in the right direction at node number 3. If we are doing this, then it will be like this: 1, 2 and 3. This is our first rotation. And after that, we have to rotate the tree in the left direction at node number 1. Now it will become 2, 1 and 3. Now we can check the balancing factor, that is 0, 0 and that is also 0. That means tree is balanced. Now we will discuss about the insertion operation in an empty AVL tree. If we talk about the time complexity, insertion is performed in order of log n time. And always when we are inserting a new node, that is inserted as a leaf node. Leaf node means that has no child. And for insertion, we will follow these 4 steps. Whatever value we are inserting, we will insert according to the BST insertion logic. And what is the logic? Whatever value we are inserting, we will compare that value from the root node. If it is less than, then we will come to the left subtree. If it is greater than, then we will come to the right subtree. And finally, we will find out the suitable location and tree and node is inserted as a leaf node. After insertion, we will check the balancing factor. We will check whether tree is balanced after inserting that particular node. As we know, balancing factor means height of left subtree minus height of right subtree difference should be either 0, 1 or minus 1. If we are getting these value, that means tree is balanced and there is no need for the rotation. If you are getting the value other than these three values, then we have to apply the suitable rotation as we have discussed in the previous slides, so that tree is balanced. Now we will understand with the help of an example. For example, we have to construct an AVL tree, and in that tree we have to insert numbers, for example, from 1 to 8. So first of all, when we are inserting 1, then we will check the balancing factor. Balancing factor is 0, that means tree is balanced. After that, we are inserting 2. Then after inserting 2, tree will be like this. That means 2 is greater than 1, then 2 will come into the right side of 1. After each insertion, we have to check the balancing factor. The balancing factor for 2 is 0. Balancing factor of 1 is height of left subtree, that is 0. Height of right subtree, that is 1. 0 minus 1 minus 1. That means still we are getting these three values, 0, 1 and minus 1. That means tree is balanced. After that, we have to insert 3. Already we have inserted 1, then 2. Then according to binary search property, 3 will be the right child of 2. After inserting 3, tree will be unbalanced at node number 1. How we can say? We can again calculate the balancing factor. The balancing factor of 3 is 0. 2 is height of left subtree. Height of right subtree, that is 0 minus 1 minus 1. For 1, height of left subtree, that is 0. Height of right subtree, that is 2. 0 minus 2, that is minus 2. That means, according to this situation, tree is unbalanced at node number 1. And tree is unbalanced due to insertion of node 3. And it is unbalanced at node number 1. Then we will, from that node, we will go to that node, that is the right of this, 2 is the right of 1 and 3 is the right of 2. If we are getting 2 odd, as we have discussed in the rotation, then in that case, left rotation will be applied. If we are rotating in the left side, then tree will be like this. 2 will become the root, 1 will become the left side and 3 will become the right side. Now after rotation, we will check the balancing factor. The balancing factor for node 1 is 0, node 3 is 0, and for node 2, that is height of left subtree, that is 1, height of right subtree, that is 1, 1 minus 1, that is 0. That means tree is balanced. Now after that, we have to insert 4. Now in the given tree, already we have this tree, 2, 1 and 3. And after that, we have to insert 4. Then for inserting 4, we will compare 4 with the root node, that is, we will compare 4 with the 2. 4 is greater than 2, that means we will come to right side. We will compare 4 with 3. 4 is greater than 3, that means 4 will be the right child of node 3. Now after that, we will check the balancing factor, whether tree is balanced or not. For 1, balancing factor is 0. For 4, is balancing factor is 0. For 3, height of left subtree, that is 0. Height of right subtree, that is 1. 0 minus 1, that is minus 1. That means it is balanced at node number 3. We will check it for node number 2 also. That is height of left subtree, that is 1. Height of right subtree, that is 2. 1 minus 2, that is minus 1. Again, we are getting these three values, that is 0, 1, minus 1. That means tree is balanced. After that, we have to insert 5. Already we have this tree, that is 2, 1, 3 and 4. And according to binary search property, 5 will be the right side of 4. After inserting 5, we have to check whether tree is balanced or not. For 5, balancing factor is 0. For 4, balancing factor is, that is 0 and this height is 1, 0 minus 1, that is minus 1. That means it is balanced at node number 4. We will check for node 3. The height of left subtree at node 3 is 0 and that is 2. 0 minus 2, that is minus 2. We can check for the node number 2 also. That is height of left subtree at node number 2 is 1. That is 3. 1, 2, 3. That is 1 minus 3. That is minus 2. That means in this case, tree is unbalanced at node number 3 as well as node number 2. If tree is unbalanced more than one node, then for balancing, always we will follow the bottom approach. That means, first of all, we will rotate the tree at the bottom level and after that, next level if there is a need. Now, in this case, tree is unbalanced when we inserted the value 5 and it is unbalanced initially at the node number 3. Then again, we will do the same thing. From that node, we will go to that node due to which tree is unbalanced. That is, 4 is the right child of 4 and 5 is the right child of 4. If there is 2R, then we will rotate the tree in the left direction and after the rotating, tree will be like this. That is 2, that is 1. Now here we are rotating in the left side. That means 4 will become the root, 3 will become the left child and 5 will become the right child. Now we can check the balancing factor. Balancing factor of node 3 is 0, 5 is 0, 4, 4, 1 minus 1, that is also 0, 0, that is 1 minus 2, that is minus 1. That means now tree is balanced. After that, we have to insert the value 6. And according to binary search tree property, 6 will be inserted here. Now, after that, we have to check the balancing factor. That is, for 6, we are calculating that is 0. For 5, that is height of 5 is 0. Right subtree is 1, 0 minus 1, that is minus 1. For 3, because it's a leaf node, there is no left child and right child, the balancing factor is 0. If you are calculating at 4, that is height of left subtree is 1, height of right subtree is 2, 1 minus 2, that is minus 1. If we are calculating this at the node number 2, because for 1 it is 0, there is no left and right child, then at node number 2, height of left subtree is 1 and height of right subtree is 3. 1 plus 1 plus 1, 3. That is 1 minus 3, that is minus 2. Now, according to this situation, tree is unbalanced at node number 2. Tree is imbalanced after the insertion of node 6. Now, again we will do the same thing. With tree is unbalanced, we will go from that node to that node due to which tree is unbalanced. That is the right of this, okay, and that is the right of this. We have to do the 2 times. That means we are getting 2R. We will rotate the tree at node number 2 in the left side. If we are doing this thing, then it will be like this. 4 will become the root because we are rotating the tree at 2 in the left direction. 2 will come as a left child of 4 and 1 come this side. Then 5 will come up this side and 6 will come this side. Because we are making 4 as a root node, then in that case 3 will become disconnected from this node. Now, according to binary search tree property, 3 will be the right child of 2. Because according to binary search tree property, at each node, its value should be greater than from the left side values and should be less than from the right side values. Now we can check the balancing factor. Balancing factor for 1 is 0. This is 0. This is 0. That is minus 1. 1 minus 1, 0. 2 minus 2, that is 0. That is tree is balanced. After that, we have to insert 7. Because according to question, we have to insert 1 to 8. Then definitely 7 will come this side. And again, we have to check the balancing factor. Balancing factor for 7 is 0. For 6 is, that is height of left subtree, that is 0. And height of right subtree, that is 1. 0 minus 1, that is minus 1. If we calculate this balancing factor at 5, then height of left subtree at node number 5 is 0. And that is 2. 0 minus 2, that is minus 2. If we calculate this side, that is 0, that is 0, that is 1 minus 1, that is also 0. If we are calculating at node number 4, the height of left subtree, that is 2 and that is 3. 2 minus 3, that is minus 1. Now, according to this scenario, tree is imbalanced at node number 5. It is imbalanced when we inserted node 7 here. So then again we will do the same thing. We will go from that node to that side. That is right of this and then right of this. If we are getting 2R, then again we will apply the left rotation on which tree is imbalanced. If we are left rotating, then tree will be like this. This is unchanged. Now here we are rotating the tree in the left direction at node number 5. Then definitely 6 will become the root, 5 will become the left side and 7 will become the right child of 6. Now we can check the balancing factor. The balancing factor of 1 is 0, 3 is 0. That is for 5 it is 0, 7 it is 0. For 2, 1 minus 1, that is also 0. For 6, 1 minus 1, that is also 0. For 4, height of left subtree is 2. Height of right subtree is 2. 2 minus 2, that is 0. That means tree is balanced. Now after that, we have to insert value 8. And according to BST property, 8 will be the right child of 7. Then we can check the balancing factor. Balancing factor of 8 is 0. For 7, height of left subtree, that is 0. Height of right subtree, that is 0 minus 1, that is minus 1. For 5, it will be 0. For 3, it will be 0. For 1, it will be 0. That is the leaf nodes because there is no left and right child. If we are calculating at 6, height of left subtree is 1. Height of right subtree is 2. 1 minus 2, that is minus 1. In the same way, we can calculate for 2. That is 1 minus 1, that is 0. If we are calculating at node 4, the height of left subtree is this one, that is 2. And for this, that is this one. 2 minus 3, that is minus 1. We are getting everywhere 1, 0, minus 1, that is tree is balanced. Now we will take one more example. And in this example, we have to construct an AVL tree and the values, we have to insert these values and we have to insert these values in the following sequence. So first of all, we have to insert 50. So 50 is balanced because balancing factor is 0. After that, we have to insert 20. We will compare 20 with 50. Then in that case, 20 will be the left child of 50 according to binary search property. Then we have to insert 60. Then in that case, 60 will be compared with the root node, that is 50. Because 60 is greater than 50, then it will be the right child. And after each insertion, we have to check the balancing factor. If we are calculating the balancing factor here, then in that case, for 20, balancing factor is 0. For 60, balancing factor is 0. And for 50, height of left subtree minus height of right subtree, that is balancing factor is also 0. After that, we have to insert 10. If we are inserting 10 in the given tree, then definitely, that is 20, my mistake. So 10 will be the left child of 20. Then after inserting 10, we will check whether tree is balanced or not. For balancing, we will check the balancing factor. So for 10 it is 0, for 60 it is 0. If we are calculating at node number 20, that is 1 minus 0, that is 1. For 50, that is 2 minus 1, that is 1. That means tree is balanced. After that, we have to insert 8. If we are inserting 8, then tree will be like this: 50, 20, 10, and 8 will be the left child of 10. Now after inserting 8, we will check the balancing factor. Then for 8 it is 0. For 10 that is 1 minus 0, 1. For 20 that is 2 minus 0, 2. That is 0. 3 minus 1, that is 2. That means tree is unbalanced at node number 20 as well as node number 50. Always for balancing, we are following the bottom approach. That means first of all, we will rotate the tree at the node number 20. Our tree is imbalanced after insertion of value 8. Then from that node, we will go to that side node. That is the left child of this, and this is left of 10. We are getting 2L. That means we will apply the right rotation at node number 20. Then after rotation, tree will be like this: 50, that is 10. So 10 will become the root. Then it will be 20 and it will be 8. If we calculating the balancing factor was needed, then for 8 it is 0. For 20 it is 0. For 60 it is also 0. For 10, node number 10, 1 minus 1, that is also 0. For 50, 2 minus 1, that is 1. That is, tree is balanced. After that, we have to insert 15. Now, according to binary search property, we will compare 15 with 50. Then definitely 15 is less than 50. Then we will come to the left side. Then we will compare with 10. That is greater than. Then we'll come to the 20. That means 15 will come as the left side. Now after insertion, we will again check the balancing factor. The balancing factor will be, that is 0, that is 1, that is 0, that is 1 minus 2, 1. That means tree is balanced. We can see with the help of this animation. So first of all, we have inserted 50, that tree is balanced. Then we have inserted 20 as a binary search property, tree is also balanced. Then we have inserted 60, then tree is also balanced, that we have seen in the previous slide. Then after that, we have inserted 10, then tree is also balanced. Then we have inserted 8, and after inserting 8, tree is unbalanced here. Then we have applied a right rotation, and after rotation, tree is like this and tree is balanced. And we can say, after calculating the balancing factor at each node. After that, we have to insert 15. Then 15 will be the left child of 20. And we will check the balancing factor. That is 0, that is 1, that is 0, and that is 1 minus 2, that is minus 1, and that is 0. If we are calculating at 50, the height of left subtree is 1, 2, 3, that is 3 minus 1, that is 2. That means tree is imbalanced at node number 15. Now it is imbalance due to the insertion of node 15. Then we will go from that node to that side. That is left of this and that is right of this. That means double rotation will be applied. In that case, we will rotate the tree left at the 10 and then right at the 50. And after this rotation, tree will be like this. That is, tree will be balanced. After that, we have to insert 32. Then according to binary search property, we will compare 32 with 20, then 50, then 32 will be the left child of 50. After that, we have to insert 46. According to binary search property, 46 will be the right child of 32. Then after that, we can check the balancing factor. The balancing factor for 8 is 0, 15 is 0, that is 1 minus 1, that is 0, 0 minus 1, 2 minus 1, that is 1, 0. For this 2 minus 3, that is minus 1. That means tree is balanced. After that, we have to insert 11. According to binary search property, 11 will be the left child of 15. Again, we can check the balancing factor for each node. That is 0, 0, 0, 0. For 15, it is 1. For 10, it is 1 minus 2, that is minus 1. For 32, it is 0 minus 1, that is minus 1. For 52 minus 1, that is 1. For 20, that is 3 minus 3, that is 0. That means tree is balanced. And finally, we have to insert 48. And according to property, 48 will be the right child of 46. Now we have to check whether tree is balanced or not. So we will check the balancing factor for each node. That is, for 8 it is 0. For 11 it is 0. For 15 it is 1. That is height of left subtree minus height of right subtree. That is also 1 minus 2. That is minus 1. For this, that is 0 minus 1, 0 minus 2 minus 2, 3 minus 1, that is 2, that is 0. And for this 1, 2, 3 and 1, 2, 3, 4, that is minus 1. That means our tree is unbalanced at node number 32 and node number 50. So first of all, we will balance it node number 32. It is imbalanced at node number 32 after insertion of 48. Then we will go from that node to that side. That is right of this and that right of this. Then we will rotate it at the 32 at a left direction. If we are rotating, then it will be like this. Now we can, that is 46 will become the root, 32 will be the left child and 48 will be the right child. Now we can check the balancing factor. For 11 it is 0, for 8 it is 0, for 32 it is 0, 48 is 0, that is 1 minus 1, 0, 2 minus 1, that is 1, 1 minus 0, that is 0, 1 minus 2, that is minus 1, 3 minus 3, that is 0. That means tree is balanced. Thank you.